Now this is my Breadbin C64. We've seen it before on this channel. Over Christmas and the New Year we got this wonderful green case and we put the Breadbin PCB into it, but the Breadbin has been not working and we didn't actually manage to fix it because we had conflicting results from the various testers. You will see behind me that this machine is currently working, and the reason for that is I sent it off to my pal Steve at 8-bit Retro Refix and he put a fresh pair of eyes on it and managed to spot the problem that I was going round and round and round in circles and didn't manage to see. Yeah, it was the RAM. But that wasn't the entire problem, because as some of you pointed out, the CIAs were not counting up their timers, and indeed these are the CIAs out of the original machine and they're a bit dead. So yeah, these are blimmin' expensive, by the way. What about this RAM? Now I tested this RAM and I showed you before the RAM tests testing it, and all these chips tested fine. In fact, these actual chips came out of a working plus 4, but they don't work in this machine. So I started thinking, is there a way that we can test these RAM chips and actually show that one or more of them is faulty? Now there are some very expensive retro chip testers out there. There's the Backbit one, which comes from the US. There is the Retro Chip Tester Pro from the Computer Museum in, I think it is the Netherlands. They are very expensive, and certainly on this channel I can't afford to get one of those. So I've been looking at alternatives. The original RAM tester that I used was a little ESP32 based board. I was looking online to see what else there was around. There were some Arduino based chip testers, and this is one of them. It's basically a shield, takes the chip, it plugs it into an Arduino R3, and it has a display of a 2-line LCD. And that went through, and I'll show you that going through. It actually has quite a nice display that tells you what it's doing, and it does a bunch of different tests, and I will give you the GitHub link to that so that you can check it out for yourself. It has a red light and a green light, and the red light comes on if it fails, the green light comes on if it passes. Then there is also this. This uses an Arduino Nano, and it's built in, and I've built it on this basically shield PCB prototyping thing. You can see it's just wires hooked up, and that is programmed. This uses an algorithm which is called March C-, and I will put a link to go through that and show you exactly what that does. And this actually did find the problem chip. This one passed everything. Happy as Larry, no trouble at all. And of course I know that it doesn't work. I'll run through these tests with some of these chips, and we'll see that, you know, it does actually thing, and the machine itself now works. We have got one other issue, and that is the CPU in here is the 6510 that I have nicked out of my 64C, and while it's in here there's no CPU in there, so I need a new CPU for the 64C. Well, actually it's going to go into here, and I'm going to make one of those, and I'm going to make an adapter that uses a 6502. Oh, there is still a fault with this, and I don't quite know what it is. and it's not showing up at the moment, but if I leave this machine on for say an hour, it will crash and it will lock up. So I think it's something that's heat related. I'm suspicious that maybe it's the ROM. So I put Jiffy DOS into the 1541 that I fixed last week. So maybe I can put Jiffy DOS into this, and that will serve a purpose of having end-to-end Jiffy DOS, and it will also maybe show that the kernel ROM is faulty, if the kernel ROM is faulty. This video is a little bit bitty, I'm afraid, but you know, odds and ends, we have to do odds and ends from time to time, and let's get on with it. We've all used solderless breadboards or designed circuits on bits of perf board or proto board like this, and that's all very well, but there are disadvantages to this. The wires can fall out, it can be messy, it can be hard to build, and for just $5 and almost as quick, you can get your own PCBs from our sponsor PCBWay. Now these are all PCBs that I have designed on the channel and shown and used, and they all work. They cost just $5 for 10 boards, and they were here in a week. So by the time you finish getting your components for this, and you've found the wires and you've reconnected them and they've fallen out and they've come back in again, you've got your boards. Do it. Check them out, www.pcbway.com. Oh, and they also do CNC machining, 3D printing, sheet metal work, all that other stuff. So you know where to go. Okay, this is the original RAM tester. It is called a 1-bit DRAM tester, and this is a Rev 3. They go up to, I think, to Rev 6 currently. Copyright 2021 Simon Raybould. I got this off eBay probably a couple of years ago now. So you put your DRAM chip in here, and it takes several different DRAMs, but a 4164, which these are, 4164 goes into this socket here, which I have marked with a little spot. You press the button, plug it in, press the button, and the LEDs flash, and it takes about 30 seconds or so, I would guess, and then the results come up. So there is a web page for it, and here it is, athena.cyraybold.net, 1-bit DRAM tester Rev 6. I couldn't actually find a manual that directly spoke to the Rev 3, but I think basically the Rev 6 just has an extra socket to do extra things. So supports most 1-bit DRAM devices from 4K up to 1024K, presumably in the 18-pin socket. The LEDs will show which of the blocks are working, and therefore if the part could be used as a smaller RAM. So that is useful for block-based things, because I believe Spectrums were, for example, used only the lower half of the RAM. So if the top half was faulty, then that was going to be fine. So these are the tests. So you can be sure that if a part tests as good as in this tester, it should work well in a real application. Well, realistically, if it passes in this, it tells you it passed in this. It doesn't tell you that it's going to work. Whereas if it fails, then it tells you it's failed. So there's a bunch of errors that it won't pick up, but that's basically what it does. So let us take one of the previously passed chips, stick it in here. Let's plug this in. Right. Press the button, off it will go. And that has passed. Unplug it. So this chip, you may see I've marked it with an X, because this is the one that I suspect is actually faulty. Once again, plug it in, hit reset. And it has passed. So on that basis, I felt it was happy to put these chips into the 64, and of course we saw what happened there. Right, I'm leaving this separate just so that it's easier to find it. Right, I could go through all these other chips, but I won't. I have already done it off camera. They will pass. The next tester, this is based on a shield for an Arduino Uno Rev 3. You may have seen this tester used before on Jan Beta's channel. He had a proper PCB made for it. It has got a 2-line screen attached to it. This is just a I2C. So I didn't have any ZIF sockets at the time that I built this, and so it's got an ordinary socket in it. But other than that, it is final. Here we are. It's called the DRAMArduino, and it's by this guy called ISS. It's a simple, very handy DRAM chip tester. It works with 4164 and 41256 ICs. Testing is not too fast but acceptable. 4 passes are performed in about 80 seconds total. Results are 100% reliable only if the test fails. You can throw away the chip without fear. If the test passes, this doesn't certainly mean it will work, because as you know, and this is about Oryx, but it applies to C64s as well. C64s are very sensitive to DRAM. So to use it, you put the chip in the socket, press the reset button, wait until the green LED blinks. If it remains on, chip is okay. If it goes bad, the chip goes red. And that's the circuit. Basically, it just connects the pins to the Arduino. I'll take this off, just so you can see underneath. So it connects the pins to the Arduino. It also connects the LEDs. So there is some software that you can download, a sketch for the Arduino. You program that in a normal way using the Arduino IDE. So that's Jan Beta's video if you want to watch it. If you want to watch it, click on this. I will post a link to that and put it in the corner. There you go, you see, version with this. So that's what we've got. I believe it does similar tests to that one. So let's just pick a different chip, stick it in. Now remember, this is USB Model B. Right. So this is going through and it's doing test pattern 1. The light flashes while it is going through, and it's now doing test pattern 10, which that's actually a pattern 10. So it's writing a 10 and expecting to get a 10 back. That's so that it checks for sort of cross-contamination. Now it's writing all ones, so 11, 11. Okay, good chip. This is our chip marked with the X. And off we go again. There we are, it passed good chip. Now remember, that doesn't mean it is going to work, it just means that it didn't fail. So this third one is called the AVR DRAM Tester by Trevor Makes. And once again it supports 4164 and 41256s. This uses an Arduino Nano and it runs something called the March C- algorithm. And it also has a read mode for measuring the row access time, so you can check the speed of the DRAM on it as well. And there you'll see a picture of it. Looks remarkably similar to this, except I've made a little breakout board for the LEDs instead of what he's done. And that is basically the circuit diagram for it. Schematic. So I'll put the link, all the links to these in the description. So to use it, right, disconnect power, etc. DRAM type is detected automatically. Full test takes 1.3 seconds. Now remember, this one took about 80 seconds and this one took about 20 seconds. So very fast. And 7.5 seconds for the 41256. If no errors are detected, the green LED will set and the chip can be considered working. The test repeats in a loop and can be left running to catch intermittent errors. If an error is detected, the red LED will persist until reset, even if subsequent tests pass. It uses platform I/O instead of the Arduino IDE, so VS Code, but otherwise you just build it and send it to the Arduino as you would for any other project. So once again we stick our suspected working device in there and we plug it in. And that's interesting, it says it's not working. So let's find another one. This is the one we used in our first test that passed. Green. So that has passed. The cables tend to push these things around. So this is the one that I've marked with a cross. And yeah, you see that comes up with a fail on this tester. In order to get this 64 working, I had to take the CPU out of my 64C, and so that has left me short of one 6510. Now 6510s are sort of fairly expensive on the eBay market, and I don't have any, but I do have a bunch of these. This is a 6502, in fact it's 6502A, and I have got this, which is an adapter to take a 6502 and convert it into a 6510. In fact, this will convert it into a bunch of different CPUs, and if we look on the back, you'll see that there are a bunch of jumpers that we can use to set 6510 or 8500. The 8500 is the 64C variant of the 6510. It's HMOS rather than NMOS. Apart from that, it's identical, and it just goes wrong even more than the 6510 does. Also, you can jumper it as a 6510T. That is the variant that is used in the 1551 disk drive. It has a difference in the GPIO, I believe. And also you can jumper it as a 7501 or 8501, which is the NMOS or HMOS CPU that's used in the Plus 4 and C16, and you can jumper it as an 8502, and the 8502 is the CPU that is used in the Commodore 128. So this one little board can be used to convert a 6502 into any one of those processors, and essentially the difference is that these other processors, the 7502, 6510, etc., have a data direction and GPIO register in the first two bytes, i.e. byte 0 and 1. And the different CPUs expose different variations or different combinations of that 8-bit register. So the 6510 only has 6 bits of that 8-bit register, for example. So I thought I would give this a go. This came from New Zealand, and even with shipping from New Zealand, it was still cheaper to get this and use one of these than it was to pay the scalpers on eBay. So let us build this up. We've got a socket, we've got some pins. The idea is the pins go in the underneath and the socket goes on the top, and we set the jumpers. Now the 6502 goes in, release the socket, goes in the middle set of pins. I don't know why I'm doing that with that, but goes in the middle set of pins. There's the notch, like that. Over the top of all the chippy bits, and then depending on the CPU we want to emulate, the pins to connect it onto the motherboard go in either that side or that side. So let's get our solder. The way to do it is, first of all, there's some instructions on here. 6502 socket is middle pin rows. Solder a pair of 20 pin headers starting at the letter for the desired chip. Solder the jumpers, then the headers, then the 6502 socket on the top. So we start first with the jumpers, then we put these headers on. And the jumpers we want for the 6510 is jumpers A and headers D. So headers D is that side and to that end. There are actually more pins. Sorry, there are actually more holes than there are pins. So D and E are offset by 1. Right, so we want jumpers A. I'm going to spray this with some IPA just to get rid of any grease. I filled up one of the holes, we can't have that. There we go. Now these go into, let's double check, headers D. So that's this side. And then I'm going to use a piece of breadboard basically to, there we go, to hold everything down at the right angle. And before I solder that, I'm going to go and double check that this is in fact the right way around. Okay, that is right. So I'll put a link to this in the description so you can get your own. There's a GitHub for it as well, so if you want to make your own, then you can make your own, either do your own SMD soldering, or you could get it assembled by PCBWay, etc. I have got a second one of these because I want to put one in my Plus 4, which has still got no CPU in it. There is an extra little jumper here, jumper W. That is actually connected. You can't see because there's solder mask in the way. But it does say here, cut jumper W if you're using a W65C02. Leave it connected otherwise. So we're using a regular 6502. I do have a 65C02, but I'm planning to use that for something else. Right. I've done it again, I've filled a hole. So I'm going to have to clean that out. And again. Okay, so it's just those two holes to clear out. I think the technique was to hold the soldering iron as close to vertical as possible. So the final part is to put the socket into the middle set of pins, like that. Now we'll double check again that that is the right way around. So we're less worried about going into the holes this time round, but I'm still going to do the corners. Okay, that looks okay. I do apologise for the camera losing focus during that soldering. But one of the problems with AI is it tends to focus on anything it thinks is a hand rather than anything that is actually useful. So I think that should be done. Let us stick the CPU in. I've got my bracelet on. There we go. Right, so let us take this apart and fit the new CPU. And what did I say when I fitted this thing at Christmas? This was going to keep falling out, and it keeps falling out. What a pain, what a pain. So that can come out and that will go back into the 64C. Stick that on there for now. Oh, that's close, that's tight. There is a gap, but that is close. So while I've got this open, we can see what I have done for the CIAs. Now I had to replace both of them and fortunately they were already socketed because this entire board has been socketed. That is a very old 1984 CIA that I had ready for something else, and this is a JCIA, which is a CIA replacement, and again I needed that for some other project, but I've had to take it out and basically put back the other project. In fact, both of these were for another project. So these are the originals that came out. They've got the blue heat sinks on the top. I'm going to recover the blue heat sinks because they are reusable. These were the original CIAs from in here. And yeah, you can see they did test okay at some point. So they've both died. So much on this board has died except for the SID. And it's ironic because SIDs are supposed to die more often than anything else. The PLA did not die, but it's been replaced because I put this in to test it and that split the pins wide open. So the old one wouldn't fit back in. You know, I really didn't want to unsolder that socket and put another socket in. I don't want to keep unsoldering stuff if we don't have to. Right, let's plug it in and try this new CPU. I'm going to shove that up there. Oh, one thing I want to do is replace the kernel ROM. We still haven't found out why it crashes after several minutes. Is it one of the ROMs? Possibly the basic ROM. Is it something in the timing circuit, in the clock generator? Where's the clock generator? I think it's in here, under that. That's a possibility. So we need to look at that. But I want to replace the kernel ROM with Jiffy DOS. And so I'm going to put a multi-changer ROM in here, which is going to operate off the restore key. I've got that to fit. Okay, so we're ready. Right. Switch on the plug. Here we go. 3, 2, 1. Yay! So our replacement CPU works. It's proof it's all still in there. But already it's crashed. Now that took no time at all. This time it's working. I'm going to go by the assumption that the problem is in fact the basic ROM, because I've got a basic ROM that I can put in. And so let's put in a new basic ROM and see if that is going to make a difference. Here is our replacement basic ROM. So this one is basic. Strappy strap. And let's put this in. This is a 24-pin EEPROM. It's a good old classic W27C512, but it's in this square package so that it will actually fit into the profile of a 24-pin chip. And it's all configured already for us, so all we need to do is plug it in. This came from eBay. Seems to be, I reckon, a good idea. So that's basically all we need to do for that. And then we just plug it back in. Switch it on, switch it on. And it's powered up. It's going. But now really we have to wait and see whether it still goes wrong. Hopefully it doesn't, but it's going to be a waiting game. So in less time than it took me to download the SD card from the camera, it did that. So it isn't the basic ROM. I'm going to put the original CPU back into my 64C, and we'll just make sure that it still works. So here it is. Don't worry, I do have all the screws. Power it up. And yep, that is working. Okay, that's working. Now, I've got an idea. We still have these two CIA chips, and since they are socketed, why don't we just swap them out and see if they actually do work. Okay. Now, I'm not doing that up tight, it's just enough to hold it. And in fact, I'm going to take this out so that we can use the diagnostic harness. Okay, so we have everything. Let's power it on, see what it does. Oh, now that's interesting. We've got numbers changing. Well, that's a pass. So I reckon those CIAs are actually working. Now that's interesting. So we're back to the Breadbin. It's running through the diagnostic. The diagnostic is fine, but it's reporting the two CIAs as being faulty. And we have this 0 value on there. Now, I don't actually believe that the CIAs are faulty because they've been put into the 64C and they work, and indeed the originals, which also reported as faulty, have been put into the 64C and shown to be working. So I think there's something else on this board that is giving us those results. If I leave that running long enough, it might crash, which is interesting. I'm kind of looking at the PLA. The reason I'm kind of looking at the PLA is because this GAL based board had square pins in it, and I didn't notice until it was too late. It has stretched the socket, and I wouldn't be surprised if it's not making very good contact. Certainly we can't try a different PLA, and I have got a different PLA. So what I think I'm going to do is, if my suspicion of, and quite frankly we're now looking into the realms of it's a bad contact on one of the sockets, or there's a dry joint or something on the back. So we're going to have to take the board out of the case. I think I'm going to replace the socket on that and also dismantle this GAL PLA. Let's turn this off and let's just take out this and look at it. So unplug it just to be safe. There we go. So this has got square pins, which is really not very good news. They're also not particularly straight. And actually, looking on the back, these two pins here don't look to have been soldered properly. But in order to replace these headers, I'm going to have to take the GALs out and desolder the sockets as well anyway. So basically I'm going to have to completely disassemble this board, rebuild it, take this socket out, put a new socket in, and then I think we shall see if that actually was the problem, or if I'm barking down the wrong tree. So this is going to be a long video, and this is going to be, you've seen me taking sockets out and stuff before, so we will come back when it's done. So this is just a simple test with the MOS PLA that may have even come out of this machine. I'm not entirely sure. Diagnostic cartridge, no harness, no SID. Let's just see if it fires up. It's kind of crashed at the screen RAM bit. Okay, it's getting further. Not too worried about the bad bits, but notice we're still getting nothing there. Okay, that was a bit of a long shot because I wasn't positive that that PLA worked. So I'm going to go and repair that GAL PLA, and we'll come back and try that out. Okay, so this is the redone PLA. It's got proper gold thin contacts, so that should go into here and hopefully it's going to work. There we go. For sure it is not going to damage that socket. So let's hook this back up again. Once again, I will just put the diagnostic cartridge in and not the harness for now. Okay, right. Let's do this. Okay, so it's not the PLA, and it's not the PLA socket. Let's just put the harness on and run through with everything actually connected. Right, so that's the harness. Let's do the test. And that's interesting. Do it again. Came up fine that time. When I say it came up fine, it looks like it's crashed. That's better. The control port will be bad because the SID is not in, so that's fine. I'm not sure why it thinks the user port is bad, because I don't believe that there is a problem with those CIAs. So what to do? At this stage, I don't really know. Should I just say, oh stuff it, and go and get a 60 clone board? $35. And basically rebuild the thing from the ground up, because something is wrong in the state of Denmark. And literally, apart from the clock circuits in here, because I don't have the chips for that, every single thing on this board, every single IC on this board has been replaced, and it still don't go. What do you reckon? 60 clone? Do you have an idea of what might be wrong? If you know, if you think, aha, I know what this is, then please tell me in the comments. Otherwise, if you've got this far, thank you for watching. Please check out my Patreon if you would like to support me in that way. My patrons are scrolling up the screen, and I will see you next time. See ya. Bye.